Hey everybody, thanks for tuning in again. If you guys haven't yet seen the video on aircraft basics that I made before, go ahead and watch that and at least just skim through it and see if there's anything that you don't yet know, because all of that information is pertinent and I will be referencing it for this video on forces of flight. So let's go ahead and get into it, right? So there are four main forces of flight. This is pretty simple. This is lift, drag, thrust, and weight. Okay, lift and weight, they oppose each other, and thrust and drag, they oppose each other as well. Okay, so let's talk about alpha. If you remember back to our last video, this is our angle of attack or our pitch angle. Now, this is a little bit nuanced than just saying pitch angle, right? It's actually the angle between our chord line, right? So if you remember our chord line here, and the relative wind. So let's say, for example, our relative wind is coming in from this direction. Okay, so we're at a pretty high alpha. So this is our relative wind. Then the angle between the direction that that wind is hitting our plane and our chord line is our alpha. Okay, so why is this important? Well, if you remember back to our CL alpha plots, right, alpha determines our lift and our drag at any given point. Okay, so CL, remember it's little l for airfoils, big L for wings. CL alpha and our curve looks something like this. And if you remember, our stall happens here at around somewhere between 13 to 15 alpha. And right, this kind of shows how important alpha is for the coefficient of lift on a wing. Yeah. When you're looking at just coefficient of lift, the only things that change it from an airfoil perspective are the geometry of the airfoil, right? So the camber, if you remember that, as well as the angle of attack. So very, very important figure here. Okay. So this is kind of what I just said, right? Free stream relative wind. So let's have a question here, and this is a little bit of a trick question. Which direction is lift and drag acting on this airfoil? Okay, give you a few seconds to think about that. You know, is it straight up, straight back? Well, it's actually a bit of a trick question, like I said, right? So it entirely depends on the free stream airflow. Okay, lift is always perpendicular to your free stream, and drag is always parallel to it. So what that means is, as you can see here, our free stream is not flat, right? It's coming in at an angle. Okay, so this implies that our aircraft is climbing a little bit, right? Because it is going upwards into the air, and so the air is coming down on it. Okay, so remember we have our alpha here, and you'll note our lift here is not straight up, right, relative to the ground. It's actually perpendicular to our free stream airflow. Okay, and our drag is parallel to it. Okay. So that's an important thing to remember as well, especially if you have to do any math or if you're creating some sort of simulation of the plane, right? This is something I had to think about when I was looking at doing a 6 DOF sim or even the 3 DOF one. But anyway, I digress, right? But this is an important part of looking at lift and drag. So how is lift generated? Um, I'll give you a hint. This is also a trick question. Okay. Well, lift is nobody really knows. Science is a lie. Okay, nothing's true. Everything's fake. No, but I'm kidding. In all seriousness, right? There are a lot of theories out there about why lift happens, and all of them are somewhat wrong for various reasons. Okay, let's start with equal transit theory. Okay, this is the assumption that air travels over the wing's top and bottom surfaces in the same amount of time, right? And the idea is that since airfoils are curved, you have a longer distance to cover going over the top and a shorter one going over the bottom. So if you had two particles of air, right, next to each other, then this one on top would have to go faster. So V1 is greater than V2. This is V2 down here to meet up again, right? Well, this is false because air particles aren't friendly. They don't have friends. You know, these guys aren't hanging out with each other. They don't try and regroup after the wing. There's nothing that says that they have to meet up again. Let's look at kind of Bernoulli's idea. The leading edge acts as a nozzle that constricts the airflow, right? Well, this is more correct. Equal transit was very wrong. This one's kind of wrong, right? There's not really anything that restricts the airflow if we're looking at the top side of an airfoil, right? As it comes over, okay? There's no wall here. It's not really a converging nozzle, all right? So it is true that airflow does speed up over the top, but it's not necessarily because of it acting like a converging nozzle. Skipping stone or Newton's third, air strikes the bottom of the wing, creating a reactionary lift force. This is still wrong, right? This doesn't really account for stall. If you had a flat plate in the wind, this still stalls at about 15 degrees, right? And if you were just looking at air coming up and hitting it and bouncing off the bottom, then at 15 degrees, right? Who's saying that this is stalling? This should keep on climbing to like 45 degrees, right? Circulation, this is kind of more of a, well, not really. It's used a lot in mathematical proofs, the idea of circulation, but it is a very physical thing, right? So it's the idea that you have a body moving through flow that creates some amount of circulation, right? The air kind of circulates around it because you have faster air on top and slower air on the bottom. But it doesn't really tell us why that circulation happens. I mean, it has to do with the geometry, but what about the geometry makes a circulation? Um, so what we do know is that we can develop sort of a complete picture about lift, right? Nobody really knows the true answer, but we do know that there's a velocity difference on the top and the bottom. We know that there is low pressure on the top, high pressure on the bottom. We also know that there is circulation, right? This leads to circulation around the airfoil of air. Okay, so moving on here, right? What is this? Well, it's a bit confusing. Okay. So this is a plot of coefficient of pressure versus chord, right? This is x over c. So our x position over the chord. So at 0 x over c, we're at 0 way along the chord. So we're at the leading edge, right? Remember leading edge and trailing edge. At zero point 0.5, we're halfway there, 50% there. And then at 1, we're at the trailing edge, right? This plot, you'll notice, kind of has two lines on it. Why does it have two lines? It's pretty interesting. Well, this will kind of help you understand it. So let's draw a line here, all right, a blue line up here, take that all the way to the back, and then let's go ahead and take a red one here. Okay. Now what I'm going to do is I'm going to draw an airfoil. Okay, and we're going to draw it. We'll draw it up here. Note the colors I'm using here. Okay. Okay. Oh, it's kind of a stupid looking airfoil. We'll make that a little better. I don't know how much better that is, but the idea is this is an airfoil right here. Okay. Well, what this graph essentially shows us is the top and bottom surface of the airfoil. Okay, so this is the bottom surface, this line, red line that I already highlighted. Okay, and then this is the top surface here. Okay, so this shows the coefficient of pressure distribution along the entire airfoil for both the top and bottom surfaces. You'll note something weird here is that the coefficient of pressure values are flipped. You might be asking, why the heck would you flip these values around so negative is on top, right? So essentially the y-axis is inverted. Well, because you always have higher pressure on the bottom of your airfoil. So if you didn't flip the axes, then your bottom surface here would actually be on top, right? And so that'd be a little more confusing to look at. So the convention here is to flip the y-axis so that you could overlay an airfoil like this and understand that this blue line on top is your top surface of the airfoil and the red line's the bottom. And this is the coefficient of pressure along each one. So this is where that pressure differential comes in, right? And you can see how you get lift from there being a different pressure on the top surface versus the bottom. And you'll also notice most of your lift comes from the first about third or so of your airfoil, right? You have a very, very large pressure differential there, and it starts to kind of taper off towards the back third. Okay? So that's just something to look at, and this is something you're probably going to come across in your aircraft design. And it's a little confusing to look at first, and I thought it'd be useful to go through. So moving on. Let's talk about drag. We have two main types of drag. We have parasitic drag and induced drag. Okay. Parasitic drag is also known as, can be known as form drag too. That's a part of it, right? So they have form drag in this plot in place of parasitic drag. But this kind of shows that there is a minimum drag point based on airspeed, right? So as your velocity is increasing, there's a point at which you have minimum drag. Um, when you sum up both your form drag and your induced drag. Okay, so just keep that in mind. So parasitic drag, it has skin friction drag, form drag, and interference drag. All of these are known together as parasitic drag. Okay. So let's go into these individually. Skin friction drag is caused by viscous interaction between a fluid and its surface, right? Talk a lot about viscosity, especially in the last video. I love this chart over here because it shows you how shapes are affected by both skin friction or viscous drag and your form drag. So you can see this plate, this flat plate in the top here, has a lot of skin friction drag because it's a very long object, right? There's a lot of time and a lot of space for these air particles on top and bottom to viscously interact and create drag and friction on that plate. Okay. Form drag is caused by separation of flow and a low pressure region behind an object. Okay. So you can see kind of on the opposite end, we have a flat plate vertically into the wind. Now you'll note, assuming this is infinitely thin, there's no space here for on the top or bottom for any sort of skin friction drag to develop. But there will still, kind of just thinking about it naturally, there will still be some drag on this object. Well, that comes from form drag, right? There becomes a wake behind this where the airflow has been kind of pushed out of the way. You remember how a stalled airflow, I talked about this last video, has that turbulent low pressure area actually behind it of kind of like the energized flow that just sits there. And that creates a lot of drag, right? Because now you have, if you think about same principles lift, you have a pressure in front of the air of your plate here, P1, and you have P2 at the back. If um, if P2, now that you have separated flow back here, is low, which it is in a wake, then if your P1 is much greater than your P2, right, this gives you um, an amount of drag, right? Because then you, just like how lift works, you get this force pushing backwards past your plate. And that's kind of the idea behind form drag. Now you see with an airfoil, you have a mix of form drag and skin drag. I hope you can kind of see that intuitively. Now you have some dimension in this vertical direction, and you have a lot of dimension in the horizontal direction. Your sphere, right, mostly has form drag. Just because form drag kind of takes precedence here, right? I mean, you have a giant wake behind a sphere. And then your flat plate, obviously, like I said, has zero skin friction drag. There's also something called interference drag, which isn't quite so important, but it's something to think about when designing a plane. And that is interaction effects between, let's say, your wing and your fuselage, for example. Any sort of sharp corners. Let's say looking at the front of the plane, you have a round fuselage with a low wing on it, okay? So this is the front. You have your little windows here for your pilots or something if you're doing a conventional plane. So there's going to be interactions here in these kind of crevices. If you don't smooth them out, you could put a fillet on that to help with this. But these actually create drag of their own, just through the complex intersection of those parts, actually kind of creating some sort of turbulence and drag there. Okay. Induced drag, right? This is a byproduct of lift. Okay. If there's no lift, there's no induced drag. It's caused by a formation of wingtip vertices, which we'll get into, which is a huge issue with going to that 3D wing, right? In the first video, I mentioned that 3D wings have less lift than an airfoil, and that's because of these wingtip vertices, okay? But you can kind of see, this is a cool video, you'll be able to see the actual flow from these wingtip vertices. You can see them forming there, right? Those kind of spirals on either side. So you can see they're very real, they're very there, and they have a lot of effect on the actual aircraft. Okay. Right, so, and that kind of ends off our video here. The next section is aircraft sizing. So we'll go straight to aircraft sizing and then we'll go into aerodynamics. This is a very, very important section. I 100% recommend that you listen to aircraft sizing because it goes holistically into how we size an aircraft, how we choose an airfoil, constraint diagrams, weight estimates, CAD models, that sort of thing. So this is definitely, of any of these videos, this is the one I recommend watching. So thank you for watching this one, and I'll see you in the next one.